Okay, so welcome to the 7th session of SuperMap GIS training camp. So today our topic is geospatial processing automation model, which is a relatively new feature in SuperMap iDesktopX. So in previous session, we have learned a lot of tools for spatial data analysis and processing, whether it's for vector data or raster data. And although our software provides you with a lot of powerful tools to do GIS work, but sometimes maybe you would find out that when you are using the tool, there's a lot of parameters you are going to set, and if you have a lot of data to do, if you have a lot of data to process or analysis, and then and then for each of the data set, you have to use the tool you just used again and again and set the parameters for them for a lot of times. So that could be quite tedious and really takes a lot of time and effort. So in such case, we would like to create a model that can automatically complete such geospatial processing procedure once you have designed them. So SuperMap iDesktopX has provided you with such tool, and that is called processing automation. And today we're going to look at it. So first, we will have a general introduction on what is about processing automation, like what is it and why you are going to use it and how you can use it to improve the overall work efficiency in your project. And then in the second part, we would create a simple PA model that is used for land cover change detection, and will have a general understanding of how to create a tool, and later you can to create such model, and later you can design your own model based on the work you are going to do by yourself. And in the third part, first we would test. In the third part, after test the model we just created, we would learn how to save the model and share it with the others, so you can reuse it in other projects if necessary. And also we will give you some examples on the application of processing automation in actual GIS projects, so that you could have a better understanding when you can use this tool. So now let's get started. So here on the right, we have an illustration of a geoprocessing processing automation model. And here you can see this is a model that connects our GIS processing and analysis tool together, and based on our workflow logic, so that once you have created it, and it can work, it can automatically execute it and produce the final result you want. And here you can see in this model, our tool is actually made up by two parts. First is a blue rectangle, and that represents the parameters and input you used for that tool. And then there is a green ellipse followed the blue rectangle that represents the output of this tool. So a rectangle and a blue ellipse makes up a So here a blue rectangle and a green ellipse connected together represents a geospatial processing tool or analysis tool. And so here we can see in this example, we have 1, 2, 3, 4, 5, 6, 6 tools in the window, and they are connected by those lines. And here we can see that, and here in processing automation, once we connected these tools together, then the latter tool can directly use the output of the former tool, as the input, so that once we build this model, it can just get one input and execute it, and execute automatically. You don't have to say, it can execute it. It can execute automatically, and so you don't have to do some repetitive work by yourself. The model can do it and give you the final output of your design that you want. So here, it is easy for you to imagine the features or the benefits of processing automation. So first is visualization. As we said, you would draw the processing automation tool by yourself. So as we, you would draw a processing automation tool according to the workflow you designed, so that once you created the model is actually the visualization of the whole procedure you are going to take in the project. And such visualization is much easier for the others to understand, and it is for the others to understand. So here, batch process means if you have a set of data of the same, if you have a set of data, if you have set of data for a project, and you can take them in one by one, and each of those data sets would go through the model and produce automatically produce an output, so that you don't have to deal with each of the data set all by yourself. The model will do most of the work for you. And then once you as you have created such you have created such a convenient model or a convenient tool, then you can save it and export it as a tool. You can save it as a tool in your own desktop software, or you can export it. So either way, that means you can reuse that model you created whenever you want. You just need to change the input, and then the model can still do the work for you. And also, as you can export it as an independent model file, then you can share that file to the others, so that you can so that they can use the model you created in their project as well. So now let's say, where can we use processing automation? Where can we find processing automation in SuperMap products? So actually, both SuperMap iDesktopX and SuperMap iServer support the application of processing automation, and they are going to be used in different circumstances. So here, when we are dealing with relatively small size of data in our research, we would recommend you to create your model in SuperMap iDesktopX to process the data. And so here, both the input data and the output of the model would be stored in your local PC. So it's easy for yourself to have access to your input and your final result. And then if we are doing a project for a big company or for a really large GIS project, then usually there are big data involved in such project. And in such case, we would recommend you to use SuperMap iDesktop, to use SuperMap iServer, because that is able to deal with big data, and it can store the data and the output both in server storage. And so that's much efficient than doing the same work in SuperMap iDesktopX. And also, if you are using SuperMap iServer, then the model you built can be tested in the server as well. So in today's session, we would only use SuperMap iDesktopX to create our model, so that it's easier for you to have an understanding of the whole procedure, and it's easier for you to create a model in the desktop software. So now let's first have a quick introduction on the whole interface of processing automation in SuperMap iDesktopX. So once you open SuperMap iDesktopX, you can find that among all the tabs we have here, we have one tab that is called processing automation. So that one contains all the basic PA tools we need to use to create a model, execute it, test it, and also save it, or input or input it, or import a model created by the others. And here, just under this processing automation tab, you can see that in the center, we have the model building window. And this is where we're going to draw our model. And as we said before, the model is made up by different kinds of processing and analysis tools together. So to draw them, we need to find the tools we're going to use and put them in the window. And in previous session, we find all the tools, all the analysis and processing tools from the tabs at the top. But when we are drawing the model, we would usually find those tools from the toolbox on the right. And here inside the toolbox, we have around 800 tools. We have around 800 tools in total that you can use to process and analyze your spatial data. And some of them are just the same as a tool you can find from tabs on the top, but some of them are designed, but some of them are especially designed to deal with big data. So we would have a further look during the demo on how to find tools in toolbox. And once we find the tools we need in that toolbox, we can simply select them and drag them to this to the model building window and set the parameters and connect them together. And once we have done all the work to draw, this model, then we can execute or run it. And you can find the button of execute from the processing automation tab. And once a model is executed, Then on the bottom, it would automatically open a window that is called task management. So using this window, you can monitoring the status of the whole model during its execution. And if there's something wrong with it, then you can find detailed information. You can find detailed error information from the task management as well, so that it's easier for you to find out solutions and to correct the model. And now we would have a more detailed look at each part of processing automation. So the first one is the tab at the top. As we said before, first on the left of the tab, we would have a button that is used to create a new model building window. And here, you can only draw one model in a model building window. So if you want to create a new one, you have to open a new model building window. And once you have complete the model, then you can use this button to check them and also execute them. And if you want to share the model with the others, or you want to import the model created by the others, then we also have tools for import model and export model. And here, there's one thing to be clarified. Import model or export model means import an independent model file into your software, or export your model as an independent file. But if you want to save the model in your workspace, then you would save them. Then you can directly save the model, or you can choose to save your model as a tool. And if you save it as a tool, then you can simply use it as a tool, as the other tools, as the other default tools in SuperMap iDesktopX. So that there's a lot of flexibility on how you can use your model. And then also, then in the center, if you want to do some batch processing, here you can use iteration tools to iterate among data sets, so that you don't have to set them all by yourself. And also here, sometimes maybe you can't find your toolbox because you simply maybe you accidentally close that window. And don't worry, here under view, as long as you check here under window, under view, as long as you check toolbox, it would reopen the window, and then you can find the tool you need. You can find the tool you need to build. You need to use when create your model. And also we have some connection tools, right? And later we would use them. And so, as we just talked about toolbox, so here we would have a more detailed introduction on what tools we have in that toolbox. Actually, there are 4 categories of the tools here: basic tool, distributed computing tool, GeoAI tool, and customized tool. So basic tool is a general tool data set. Is a general tool set we use for data management, processing, analysis, and mapping. So all the tool we have learned in previous session actually belongs to basic tool. And then, as we said before, sometimes we would use PA model to deal with big data. And when we are using big data, there's a large amount of computation involved in, and so here we would use distributed computing data to further improve the efficiency of the computation. And so that kind of data, that kind of tool belongs to distributed computing tool. And then here we also have a specific kind of tool that is called Geo AI tool, and usually we would use them only for deep learning and machine learning, which means most of them are used for object detection from satellite data. Okay, so here we just talk about Geo AI tool. So really, we would use that one so it contains the deep learning and machine learning tool we designed for object detection from satellite image, and also it contains tool for advanced application of for some advanced application of video map. If you want to use tool, if you want to use Geo AI tool by yourself, then first you would have to set the conda environment of your computer, and also it has a higher requirement for your computer, like you should have a good GPU and CPU. You should have both a good GPU and CPU, so that you can use Geo AI tool. And so in this webinar, we won't talk about Geo AI tool, but you can learn more from our YouTube channel. And finally, the last category is called customized tool. As we said before, you can save your model as a tool. You can save your model as a tool in your desktop software, and that tool created and saved by yourself, it can be called as customized tool. And you can not only create a tool, you can not only create your own tool by save the model, but also if you are good at programming, then you can create your own tool, use Java and Python as well. And that's a really advanced skill, so we won't learn them today. So we won't talk about them today. Just let you know, here's a lot of tools you can use and create by yourself. And then let's go to what elements we have in a model. As we said before, here actually the model is made up by tools connected together. And here first, as we highlight here, a blue rectangle and a green ellipse make up a tool. And once we have multiple tools added to the same model building window, then we can connect them with those connections. And the connections is going from the output from the previous tool to the parameters of the latter tool. And then for each of the tool, if you double click on the rectangle, then you can set the you can open the window and set their parameters, like the example here. You can set the data set you used as an input, and then also you can set all the tool parameters as the same as what you do when you're using the tool by yourself. And also you can specify its output. And later we will draw our own tool in this software. And finally, here is a quick introduction on task management. As we said before, we can use it to monitor the procedure, to monitor the whole procedure when we run the tool, and it would show the status of each of the tools. When we run the mod, we can use tool management to monitor the procedure when we run the model, and it would show the status of each of the tool in the model. If it's waiting, that means if it's waiting, that means we're not execute this tool now. It can only be execute after we have complete all the work before it. And if it's running, that means we're just doing the work for this kind of tool, and you can see the result of it later. And then if it's failed, that means there's something wrong with the tool, and you can check detailed error message from task status as well, so that you can know how to solve the problem. And finally, if there's nothing wrong with the tool, then it would show the status of complete. You can also see in the task management, here is a little green icon before the tool. That means the tool has complete and there's nothing wrong with it. And also here is a green check mark on that tool in the model as well. So it's easier for you to going through. It's easier for you to check the status of your home model, And that's all the basic information for processing automation. And now we're going to create our new PA model. So here we would create a model that is used for land change detection. And as you all know, land cover change is always an essential topic in GIS, and it can work as an obvious indicator on how human activities have changed the environment. And so here, first, we would use the land cover data set for Florida in 2008 and 2017 as an example. So we would create a model to compare the land cover of the same area in 2008 and 2017, and then we can summarize where are the areas that have. Then we can find out where the land cover have changed in this area, and we can calculate the change area by each of the by counties. And so here, as we all know, land cover, and so here, as we all know, Florida is only one state of that country. And then if we build a land cover change detection model for the state, and then once we change the input, then we can get the land cover, the result of land cover detection for other states as well. So here, before we create the model, first we need to have a clear understanding on how to detect land cover change and summarize them, and summarize that by counties. So actually we would have three parts first one is to detect where we have where those changes happen, and then we would summarize the area, and then we would calculate the area of land cover change, and finally we would summarize it by county. And so here are more detailed steps. So first, for change detection, I think it's easy for you to understand because now we already have the land cover data for 2008 and 2017. So we can simply subtract them, and if after the subtract, if the value is 0, that means there is no change happened in that area. If the value is not 0, then that means that's where the change happens. And we would use raster reclass to extract where those changes happens or occur. Those changes happen or occur. And then as all our data is stored in raster, and we can calculate the area for each of the pixel. And then based on the area of the pixel, we can calculate the area of, we can calculate the exact area of those changed pixel, so that we can know how large the change happened, how large the changed area is. And then after we get the area of changed pixel, then we can summarize them based on the county boundaries. And the tool we used for summary, for this kind of summary, is called zonal statistic. That is to say, we would use a vector tool to summarize the value for to summarize the pixel value for a raster data set, so that for each of the feature on the vector data set, we would get the summarized result from the summarized value from the raster data set. And that's all we need to do for area summarize. And here, here's one thing you need to notice. Once we summarized the raster data set, the result we get is still a raster data set. And so we need to change it from raster to vector. And then for that vector data set, we would have an attribute field that shows the changed area for each of the county. So that's a whole process. That's a whole process for land change cover detection. And now we're going to open SuperMap iDesktopX and create our model for it. So here I have already opened SuperMap iDesktopX. If you haven't opened it, just open it now. And when you are opening it, now let me show you the data sets we're going to use for today's demo. So we have already shared the materials for today's session to you. And here, the first one is the slides of today's session. And then we have a data source that is called land change, and it contains the land cover data and also county boundaries for our study area. Okay, now I think most of you have opened SuperMap iDesktopX, and so here first we need to connect to our data source. And go to Workspace Manager, find data source, and then right-click, choose Open File Data Source. And under it, select Land Change and click Open. And under it, you can see that the first two data sets are what we're going to use for land change detection, for land cover change detection. You can double click to open them to first have a look on the data. So here we have the land cover data for Florida in 2008 and in 2017. You can simply put them in one map window and now have a visual comparison between them. Here, both of these two data sets use the same land cover index. And if you are interested about it, just go to the material. Here we have a text file that recorded the categories and key for each of them. So you can compare the land cover. So you can use this file as a reference to have a better understanding for this land cover data sets. And so here we would simply close them, and now create a model for land cover change detection. And to create that model, as we said before, we can directly go to our tabs on the top and then find the one that is called Processing Automation and click on it. Then you can see all the basic tools we're going to use to create our model. And you can see that most of them are inactive now because now we haven't opened a model building window. And to open a new model building window, just go to the left, and here is a button that is called New. Simply click on it. Then the software would create a model building window. Now here, like this one, you can see that once you open it, now most of these tools are active. And then what we need to do is add our data. Now what we need to do is to add the tools we are going to use for land cover change detection and connect them based on our workflow. And as we said before, we would find all the tools from our toolbox. And now, as we just opened a new model building window on the right, it automatically opened a toolbox window for us. And if you can't find this window, then go to Processing Automation tab, and under it, here under View, you can see that here is an option called Toolbox. Once you check it, then on the right, you should see the Toolbox window. And here we can see that it has grouped all the tools based on how they're going, based on their functions. And here, if you are not familiar with all those functions, then you can go to the top of this toolbox window and input your keywords for searching. Like now we're going to do, first we're going to find where land cover change happens, where land cover changes happen. So the tool we are going to use is called raster the tool we are going to use is called subtract. So here, once you input those keywords, the software would automatically would automatically search among the toolbox, and it's easier for you to find the tool. So here we can see that the tool we are going to use is actually under data processing for raster algebraic operation, and the operation is called subtract. You can simply select it and then drag it to our model building window. And now you can see this is how now we have ended our first tool into the model building window. And as we said before, it is made up by two parts. The blue rectangle represents the parameters for the tool, and the green ellipse represents the final output of the tool. And now we can double click on this blue rectangle, and you can see once we double click on it, on the right, we have opened a window that is called parameter settings. So here we can set the parameters for this subtract tool. So here we can see now as a function of this tool is to conduct subtract between two raster data sets. So here our first data set should be Florida. Our first data set should be Florida 2008, and then our second data set should be Florida 2017. And then here for the pixel format, we should change it to single, because we would have minus value in our final result. So here we need to change the pixel format to single instead of integer. And remember to check ignore no value cells. And we don't have to change the name for our output data set. So now we have complete all the settings for our first tool. This one would do the subtract between Florida 2018 and between Florida 2008 and Florida 2013. And then its output here, that one here in its output, where the cell value is 0, means there's no change happens. And for all the other cells that has a value rather than 0, that means there's something. That means there's some changes happens, and we need to highlight those areas. We need to highlight those change areas, and to highlight them, the tool we're going to use is raster reclassify. And so here still, you can go to the window on the right, and at the bottom, you can switch between the windows by click on those tabs. Like here, click on toolbox. Now we have switched to the window of toolbox, and then we can input the name of the tool. Now we are the name of our second tool, that is raster reclass. Here, under data processing, under tools for raster, find raster reclass, and then select it and drag it and drag it to our model building window. Here we can also adjust its position. And then now we have two tools added into this model window. And then what we need to do, as we said before, we need to connect these two tools together, and we would use the output of subtract as the input for rastery class. So to do that, the easiest way is to first put your mouse at the green ellipse of your first tool, or at the output of your first tool, and then click on your mouse and simply drag. You can see here you have dragged a line out of that output, and then simply connect it to the settings or parameter settings for rastery class. And here release your mouse, and now you can see here's two options. It asks you whether you want to use the output from the former tool as a source data set for your second tool, or if you want to use it simply as a precondition. Here, usually we would choose to use it as our source data set, and click source data set. Now you can see we have connected these tools together. And now let me see if you have any questions. Now, it is very important for you to know how to connect two tools together. So let me know if you have questions still, if you don't know how to connect them, or if you have questions on how to add those tools to this model building window, or you don't know how to connect them together. Then, okay, it seems to me that most of you have no problem on it. So our next step is to set the parameters for rastery class. Still, as we just did before, right-click on the blue rectangle of rastery class, and then here on the right, you can see now the parameter settings window switch to the settings for rastery class, and it just looks the same as the rastery class tool when we simply find it from our tool tabs. And so here, what we need to do first, we can say that for the source data set, here you can see the name of it. That means it would use the output for subtract tool. That is what we desired. And then for the other parameter settings, just first make this window bigger, make this window larger, and then here on the right, we can change the reclass model, the reclass mode. So here we would change it to reclassify unique value. And as we said before, if the cell value in the subtract output is 0, that means there's no change on it, and we don't have to focus on those areas. What we're really interested is where the pixel value are not 0. So here, first we would set. So here, when we are doing reclassify unique value, we would only keep one category. And here, the original value should be 0. And as we are not interested about it, so the value for such area, so the target value for those cells in the reclassify output should be 0 as well. And then under it, we can set unrated units. That means for all the cells with values rather than 0, that's where we are interested. So here we would set the value for those unrated units or cells to be 1 in our final result. And that's all we need to set for Rust reclassify. So once we execute this model and complete the work for Rust reclassify, the final result we'll get is a Rust data set that highlights areas where change happens with value 1, and then for where the change there's no change happens, the pixel value for those areas should be 0. And now we have find out where all those, and so now by using these two tools, we have find out where all the change happen, where all those change happens. Now we need to calculate the exact area for where those change happens. So to calculate the value of those areas, first we need to know we don't need to change. Sorry. Thank you for the remind. We need also change. We also need to change the pixel format to single as well, just so to make all the pixel formats for our output consist with each other. And that's all the settings we need to do. And then finally, and then our next step, as we said before, is to calculate the exact area value for where change happens. And so here we will calculate it based on the area of each of the pixel. And here, if we select the land cover data for Florida here, and right click to check its property. Here under coordinate system, we can see the coordinate system it's which coordinate system it used, and also we can see that the unit for that coordinate system is meter. And so here we have, as we have calculated before, as we already calculated. So here, the approximate area for each of the pixel under this coordinate system should be 89,000. And so here we would simply multiply this value with each of the pixel with value 1, so that the value of the value of our interested area, the value of pixels in those in the areas where the change happens would change from 1 to the area of each of the pixel. So here would go to toolbox and find the tool we're going to use, and the name should be multiply. So here the tool is still under data processing for raster algebraic operation and multiply. Select it and drag it to our window. And then connect it with the output of raster array class, just as what we did before. And here, as you can see, because multiply asks for two input, there should be two inputs, there should be two inputs for multiply. So here we would set the output of raster array class as the first input. So that should be data set 1. And then double click on multiply. Here we can see we would use the result of raster array class as an input. And then, as we said before, we want to use this data set to multiply the value of the area for each of the pixel in the data set. So here we would change for data set 2, we won't use a raster data set. We would use a constant value. So here first, change under data source, change it to constant value, and then input the area value for each of the pixel, and that value should be 169,000. Here, that is a value you need to input as, that is a constant value we need to use as another input for for raster multiply. You can also find this value from our slides. And for the pixel format, also we would change it to single and ignore no value cells. And we don't have to change the input for, we don't have to change the name of our result data. And now our next step is to summarize the area of change by county. And here, under our data source, you can see that we have a vector data set that is called Florida. If we open it, we can see that it's the county boundary for the state, and it uses the same coordinate system as our land cover data set. So we can summarize the area of change by each of the county using this data set. So here, first we need to add the tool we used for summarize into this data into this model building window. So here, go back to toolbox and find the tool we are going to use. That one is called zonal statistic. Here, it should be under raster analysis, and it is used for raster statistic. That tool is called zonal statistics. Drag it into the window here. You first connect it to the output of of raster multiply. So here, first we need to add the tool that is called zonal statistic into our model building window. Here, if you have added this tool into our model building window, just let me know. Or if you still have some questions for how to connect those tools or set their parameters, you can also raise them in the chatting box. Okay, now, if you don't have any questions, then let's connect the output for raster multiply to zonal statistics. And here, you can see that for zonal statistic, it also asks for two input. The one is zonal data, the other one is value data. Value data provides the value for statistic, the value for further statistic analysis, and the zonal data should be the data that is used to divide the value data into different areas. So here, the result for multiply should be our value data. And then let's double click on zonal data set, on zonal statistics. So here, let me answer a question first. For multiply, the constant number is calculated from the data from the coordinate system we used for our original raster data set, and you can calculate it by yourself, or you can measure the pixel area for your data sets in our desktop software as well. Either way is okay. It's approximate value, so there may be a slight difference on it on each of the pixel based on their area, based on their location. Sorry. And so now here, let's double click on zonal statistics and set its parameters. So now first we have, so here for value data, we have set it as the output of multiply. And then for zonal data, we need to use the vector data set that is called Florida under land change. And then for parameter settings, here the statistical field should be a unique field. That is to say, for each of the feature, the value of this field should be different. So here we would change it to GeoID. And for statistical mode, we would use sum, and also remember to check ignore no value data. And here for the output of zonal statistics, here we can see that there are two outputs, a raster data set or a grid data set. And also here is an attribute table. Here we would only use the raster data set. In this model, we can but we don't have to delete the attribute. We don't have to delete the attribute table. We can simply leave it here and only use this raster data set. So now our final step is to convert this raster data set to a vector data set, so that we will have a better visualization of our final result. So here, to do that, the tool we're going to use is quite simple. That is raster to vector. And here we can simply input the name of this tool. So that should be under raster analysis used for vector and raster conversion, and select raster to vector and add it to the model window. And for instance, if you just add a run tool here, and actually you don't want to use it at all, simply select it and then press delete button on your keyboard. Then you can delete that tool. Okay, we will have a further explanation on how to decide the constant parameter for the multiply. Now let's just continue. So here we have added raster to vector into our data into our model building window, and we would use the raster output from zonal statistics as an input for raster to vector. So connect it to this tool and use zonal statistics output as a source data set. And here we would find that first double click on raster to vector, and then we can set parameters for it. First, there's nothing wrong with the source data set. We would use the output from zonal statistics. And then for no value settings, here the no value should be -999. That is a default no value setting for raster data sets produced in SuperMap iDesktopX. And then for the raster field, that should be value. It's okay, there's nothing wrong with it. And then make sure for the result data set, that should be the data set type should be region. And then we can see that there are three outputs. From raster to vector. The first one is the actual output data set. And then if we want to do some condition, if we want, and then here are some more, and then here are some outputs, that is to say, and the other two outputs, we won't use them. For the other two outputs, we won't use them in this case. But if you are creating a more complex model, then maybe you want to know the exact. Then maybe you want to use the exact type of the output data set as the input or condition for other features as well. Or maybe you want to know if the result is converted to a specific grid. If you are doing when creating your, in some cases you would use them as the input for other tools, but here we won't use them. So now that should, or now we have added all the tools we need to use to create our model and connect them together, and also set the parameters for them. Now we will have a 5-minute break, and if you have any questions on how to create this model or how to set their parameters, you can raise them in the chatting box. If you don't have questions, just take a water and have a 5-minute break. And now I will give a further explanation on how we decide the constant value in multiply. So here first, we can open the data set, the land cover data set. Here we used as our original input. And then if we go to the properties of this data set, we can see that now we have learned what coordinate system it has used. And then if we go to raster tab, you can see that under raster resolution, here you can see the resolution means the size of each of the pixel, and it would use the unit the same as the coordinate system of this data set. So you can simply use this resolution as it's a square, as usually the pixel should be a square, to calculate the size of each, to calculate the area of each of the pixel. That is to say, 411 plus 411, and the approximate result should be 189,000 square meters. And here, if we zoomed in, we can see that here we can also find each of those pixels, and then you can measure the area of each of the pixel as well. And to do that, here it's under Maps tab and under Options. Here under Options, you can find that here are options that is called Map Measure, and under it, you can measure the area. And so here we would draw an area of this pixel here. So here you can see that this is not a perfect square that is overlaid with 1 pixel. So the value is relatively larger than the constant value we used in raster multiply. But if you want to do it yourself, you can draw it more carefully and make it perfectly overlaid with a pixel. And here, if you have a better understanding of projected coordinate system, then you might know that although here the pixels are in the same raster data set, but the area of each of the pixel may vary based according to their locations, and you can measure the area of each of the pixel by yourself. And if you measure the area of one on the very north and then the other one on the very south, then you can see that the value of their area might be there's slight difference between the areas of each of those pixels. So here we only use a approximate value as a constant, approximate constant value when calculate to calculate the area where land cover change has happened. And if you have any more questions, you can still raise them in the chatting box. And now, if you don't have any more questions, then we can execute the model we just create and to get our final output. So here, we need to go to Processing Automation tab, and then we can directly click Execute button. And now here, you can see once we click on it, here we have opened Task Management window, and here we can see the status for each of the tool. And that might take some time for the calculation of all the tool. To run the model, on the top, you need to go to find Processing Automation. And then under it, you can see that here's a button that is called Execute. Simply click on it, then you can run the model. If you click on it, but there's nothing happen, but you can see the status for each of the tool under Task Management. That means there might be something wrong with your model. Just to check your parameter settings and the connections between your tools. And here you can see that I have successfully run this model, and we can see that in Task Management under Progress, here it says 100%. That means there's nothing wrong with my model. And in the model window here, we can see that on each of those tools, here is a little green check mark. That means to run. And as we can see, all the check marks here, that means that again means there's nothing wrong with my model. And then you can see that under my data source, here it has produced all the raster outputs of this model. And here the final output should be a vector data set. And the default name is result grid to vector. And we can double click to open it. You can see that now the shape of it is the boundaries is the county boundaries for Florida. And if we want to have a better visualization of this result, simply here I can create a semantic layer for this data set. And I would here I would set it to be ranges semantic map and use the default style. Click OK. And now here for its expression, its range expression, that should be value, just to make sure. And so now that highlights the area of changes for each of the county. And you can see the darker and redder the value is, that means there is more changes happens in that county. And now, as we can see the result, so here we can see that there's nothing wrong with our model, and we can use it for further application and for how to apply and for this kind of and for the discussion about the application of PA model. So first, we would come back to our slides. Here, if you still have some confusions on how to create the model or run it, or the parameter settings, you can always go back to our slides and review on the settings for each of these steps, And finally, you can see that this is how the output should look like. And then let's see how we can use PA model in our final in our real GIST project. So here, as you might have noticed, usually we would use a PA model when we have a standard process or procedure on our data processing and analysis, and then we would use a lot of data for the same standardized process. And so the variation mostly happens in the data sets we use as an input, and sometimes we would have some slight changes on the parameters. And so in such cases, if we do it all by ourselves, we would have done repeated operations by again and again. But if we have built a model, then we can use the model to visualize the standard process, and then simply change the input of the model. Then we can have a automatically process. Then the software can automatically do all the operations for us. So here in your project, in your GIST project, you can use numerous data as the input of your model, and then build your model based on a standard workflow, and then you can use one of your data sets to test the model and to see if you get your desired result. If the answer is yes, then that means your model is executable, and then you can save it and then take in your numerous data as an input to complete your batch processing and get your result, and also share your work and your model with the others, and you can reuse the model whenever you want. And so here, when we created a model in SuperMap iDesktopX or in SuperMap iServer, either way, we can export our model as an independent model file, and then it can be imported into SuperMap iServer as well. So that gives us more flexibility in the application of the model, models. And we can also export models we created in SuperMap iServer and use them in SuperMap iDesktopX as well, because they would use the same set of tools. So that when you are testing your model, we would recommend you to use a small piece of your data sets in SuperMap iDesktopX and make sure it works, and then export it into and import it into SuperMap iServer, and then you can conduct. And using SuperMap iServer, you can complete you can run the model for big data. And now let's see some examples here for the application of PA model. For instance, here we have DM data sets for the globe, and then we can use it to calculate the slope at aspect, and so that we could have a terrain evaluation for the globe. And so here, as you might know, the DM for the whole globe would not be a single data set. Actually, it would be a lot of raster data sets it would be made up by a series of raster data sets. And so we can take that series of raster data sets as our batch input, and then create a model for our terrain evaluation. And finally, it can automatically produce the evaluation result for the globe, for the terrain evaluation result for the whole globe. And here, this is a simplified model created for terrain evaluation. And once we created it, then we can take the series. We can take a series of raster data set as an input, and so that to conduct a terrain evaluation for the globe. And then also we can also apply different models to the same set of the data sets, and then we can have the evaluation result for different aspects of the area. Like we could have like for instance, here we could have for the data sets of the same area, we could apply it. We could use it as an input for these different models, and then we can automatically get the result for agricultural suitability evaluation and ecosystem protection evaluation, and also the evaluation for urban planning suitability as well. And then we can also use all these different models for other areas as well. And so now here, in today's session, we just created a very simple model. And as we would do for all the models, we would save our model as well. And before we save it, first we need to rename the tools and outputs for it of this model. So that it would be easier for the others to understand the work of your model, and then we can export it and reuse it to detect the land cover changing in other states. So here, let's go back to our software. First is to rename the tools we used. So the first one, we can choose the first tool, the raster subtract, and right click on it. Here we can see that the first one is called rename. And so here we can give it a name as we have used this tool to find out change area. So to find out where change happens. So detect and change. And also change the name for its output. And that should be and change with. And then for the next tool, we can also rename it. And you can refer back to our slides to name all the tools and data, to rename all the tools and output in this model, so that could be more meaningful to the others. So here, to save time, I won't rename them one by one. Later you can rename them by yourself. And now, let's say how to save this model. To save this, as we said before, here's we can save this model in our workspace. For instance, now if we right click, then here is an option called Save Model. If we click on it, then we can give it a name. That should be land change detection, and click OK. Here, once we save it under Workspace Manager, here on the models, we can see that here is a saved model. Now, if we close this model and also close this map and all the window here, and now once you saved your workspace, and then if you open your workspace again and under models, you can always reopen the tool we have created, the model we have created, and we can reuse it. And also, when you are sharing, when you want to share your models with the others, maybe you don't want to share them with your whole workspace. Maybe you only want to share them with the model you created. Then here, you can first click on Processing Automation tab. And then under it, here is an option. Here is a button that is called Export Model. If you click on it, and then navigate to where you want to export this model, and still give it a name, like land change, and click Save. And then you can go to, and then we can see that under the folder of Material 7, here we'll have a XML file that is called land change. That is model. That is the model file. You can share it with the others, or open or import into iDesktopX or or SuperMap iServer. So here, for instance, we would close this map window. We would close this model building window. And then you can see that under processing automation, although other functions are inactive, we can still import model. If we click on it, and then here, go to Materials and 07, we can find the model that is called land change, and open it. Now we have import the model from this independent model file. And then we can reuse the model here. As you can see that in our data source, when not only do we have the land cover data for Florida, we also have land cover data for Texas in the same format. So here, we can simply change the input of this model, and then we can automatically produce the land cover change detection result for Texas as well. So here, there's only two input we need to change. First, double click on detect the lag. Double click on our first tool, and here for the input, for the two input data set, we would change it to the first data set would be Texas 2008, and the second data set should be Texas 2017, and we don't need to change other settings. And then the next input we need to change is in zonal statistic. Here, select it, and here we need to change the zonal data and change it to the county boundaries for taxes. That is the vector data set called taxes. And that's all the changes we need to do. And then after we have changed these two input, now we can click on execute, and the software would run the software would run the model again. And after the upon the completion, we would get the the land cover changed area summarized by county for taxes. And because this is a simple introduction for processing automation, so here we have to change the input by our hand. If you have a lot of data, here you can use, here under processing automation, you can use iterate file or iterate data sets to simply let the model to iterate among your input data sets. So you don't even have to change the input. You just have to set the iterate data set, and the model will do all the work by itself. Now let's just wait for the completion on this model. And if you have any other questions, you can raise them in the chatting box as well. Here we can see that maybe we need to wait for 1 more minute for this tool. Okay, almost, because taxes is a really large state, so it would take longer for zonal statistic calculation. We cannot directly import the model builder result from other software, because the settings for the tools are different. But you can use your previous model as a reference and create your own model in SuperMap iDesktopX. And now we can see that we have complete the execution of this model again. And now we can open the final result. Double click on it. We can see that now it looks like the boundaries of taxes. And then also we can create a thematic map for this data set. That should be a range thematic map, a thematic layer, use default. And now make sure your ranges expression should be valid. And now that's how you can see that. That is the result. That is the land cover change detection result we get for taxes by counties. And it's easier for us. And you can see that as once we created the model, we only need to change the input of the model. Then we can get the final result for another state. And also you can refer back to the slides for all the operation we have done. And that's all for today.